So in the last two videos, we have been looking at finding the average rate of change. And we know how to find it given a graph, a function, or a table. However, it would be nice that if we didn't have to average our rate of change, if we could actually find our rate at a specific instance instead of averaging it over an interval. In this video, that's what we're going to be doing. We're going to be looking at how to find the instantaneous rate of change, and we abbreviate that using IROC. So we defined the instantaneous rate of change to be the slope of the tangent line. And I'm going to draw for you what that means. But the tangent line at x equals a is a line that touches the curve at x equals a, and it goes in the same direction, but it doesn't necessarily cross or touch at any other point. It can, but it doesn't necessarily have to. This is different from a secant line because with the secant line, remember, it always goes through 2 points on the curve. So tangent lines are just going to go at 1 point. Let's look at a drawing to see if we can see this a little bit better. So here's my function f of x. It's this red curve here. And what we know how to do so far is find the slope of the secant line, where we have 2 points on our curve, and we can find the slope of that line just by using our change in y over change in x slope formula. But what we're trying to do is we're trying to come up with the slope of the tangent line, which is the actual instantaneous rate of change of our function f at this x equals a. And we decided that the instantaneous rate of change was the slope of this tangent line. So the tangent line intersects your curve at the point you're looking at, and it might intersect your curve again, but near this spot it's just touching at this 1 point. And if you were like driving a car along your curve, the direction of the tangent line is the direction that your headlights would be pointing, straight ahead. So as you turn, the direction that your headlights are pointing turns also. So if we were looking at a point up here, say maybe right here, our tangent line would look something like this. Over here, our tangent line would look something like this. Okay, but right here, this purple line is what our tangent line looks like. Now, we don't know how to find the slope of that line because we only have 1 point on that line. However, we can find the slope of the secant line. But if we choose a second point that is near our point that we're looking at, then we can find the slope of this secant line. And if we let this distance, this a plus h, move closer and closer and closer to this a, so as this point moves this way, the slope of this blue line, this secant line, is going to get closer and closer and closer to the slope of that tangent line. So as the distance between those 2 points, which is our h, goes to 0, that average rate of change gets closer to that instantaneous rate of change. So what we're going to do is numerically we're going to find the slopes of these secant lines. We can do that because we've got 2 points, and then we're going to choose successively smaller values of h. So if I wanted to find the slope of the blue line, the slope of that secant line over the interval a to a plus h, I would take the change in my y's, so that would be f at a plus h minus f at a over the change in my x's, so that's a plus h minus a. Notice how those two cancel out, and we get f of a plus h minus f at a all over h. You've seen this before. It's called the difference quotient, and you've practiced with, given a function, finding the value of the difference quotient algebraically. So what we're going to do today is we are going to find, for values of h that are getting smaller and smaller and smaller, we're going to find the value of this the slope of this secant line, this average rate of change, and then we're going to see that as h approaches 0, this is going to approach our instantaneous rate of change. Let's look at the same example that we were looking at in the last video where we were looking at the poverty rate problem. So here's my poverty rate curve that I had worked with earlier. And last time we were looking at what the average rate of change was doing as we increased from, say, 39 to 39.5 or 39.5 to 40. This time, what I want to do is I want to look at what's going on right here at x equals 40. How is our poverty rate changing right at this x value? To answer that question, what we need to do is we need to find the slope of this tangent line. But the problem is that the slope of that tangent line can't be found directly because, without doing a lot of estimating, because I only know one point on that function. So we're still going to estimate, but we're going to come up, the way we're going to estimate is going to lead us down a path of finding a more precise way of doing this. So our goal here is to find the slope of this red line. What we could do is we can find the slope of this line that goes between this point and, say, this point, the secant line between those 2 points. Notice how that line looks like it would be pretty close to the slope of this red line. So that's what we're going to do. We are going to find the slope of a secant line where the second point is close to the first point. And you'll notice that as I move this second point closer to the first point, maybe I move it to there, then our secant line becomes really super close to that red line. Okay, so again, what we're going to do is we are going to find the slope of the secant line between points that are getting closer and closer and closer to that point that we're looking at, x equals 40. So we're going to go, say, first from 40 to 41, and then maybe our interval is going to go from 40 to 40.5. This second x value is going to be getting progressively closer to the point of tangency. Finding all these average rates of change, this is a very repetitive process, and we want to systemize this as much as possible. So we're going to use technology to do this. So we already have our p of x in our y1. If you don't, go ahead and put it in. It's 0.092x squared minus 8.1x plus 190. And then we're going to quit out of here. So these directions are right down here in this area here. So we've done steps 1 and 2. Now, the next thing we're going to do is we're going to store the value of h. So in this first one, let's look at this first, try to fill in this first part of this table. Our value of h is 1. So to store a value, I first type the value, so I type 1, and then I press this store button right here, right above the on key. And then I need to tell it to store it in h. So I need to stick it in alpha mode, so I go alpha. And then over here is where my h is. It's right above the division symbol. It's that caret. And then I press enter. So I've stored my value for h. And now we're going to type in our average rate of change. So here we have f p at 40 plus h minus p at 40 over 40 plus h minus 40. And notice how these 40s cancel. So I just have p of 40 plus h minus p of 40. This is right down here is what we're going to have. In this box, we're going to have 40. So it's going to look like open parentheses, vars, y vars, function 40 plus alpha h minus y1 at 40. Now if we were looking at 5, we would put 5 there instead of 40. Close the parentheses on the numerator and then divide by h. So we end up with negative 0.648. To do this next one, the only thing that's different is this value of h. So we're going to store a new value for h. We're going to go 0.5 store H. Enter. I need to do this calculation of the average rate of change over again, but I don't have to do anything to actually compute it. I can go second, enter again to bring up that line, and just press enter once I have it. Okay, another way to get that line is to just up arrow and then press enter once you get on it. I want you to try and finish up the remainder of this table. You're back. Did you get these values for the average rate of change? Hopefully you did. So we can see that as that value of H approaches 0, the average rate of change approaches negative 0.74. So our instantaneous rate of change for our P is negative 0.74 at 40. So we have a couple ways of writing that. One way is to write P prime at 40 equals negative 0.74. And another way of writing that is writing dp dx at x equals 40 equals negative 0.74. So those are just notations that we use for this concept of the instantaneous rate of change. So let's take that, interpret that number in a sentence. Once again, we're looking at our when. So this time, instead of having our when be between two values, we're looking at our when at a specific instant. So we're looking at x equals 40. So when the median household income is $40,000. Okay, next we're ready for the what. The poverty rate, that's the what, is, let's see, it's decreasing because we're looking at a negative slope at a rate of, now this time, before when we've said this, we've said at an average rate of, but this time it's not an average rate, it's the actual instantaneous rate. So we could just say at a rate of, or you could say at an instantaneous rate of, either one, and we're going to put 0.74 percentage points, and you could either say per thousand, you could write it like that, or as we've been doing it in previous videos, we could say for each additional $1,000 in. Let's look at this again. Our big concept is that we're trying to find the instantaneous rate of change. So as H approaches 0, the average rate of change approaches the instantaneous rate of change, which is the slope of that tangent line. So as H approaches 0, the average rate of change, which is f of x plus h minus f of x over h, is going to approach the slope of that tangent, which is the instantaneous rate of change. And the slope of that tangent line equals the slope of the curve, the instantaneous rate of the change of the curve. A new terminology here, we say the derivative of f of x, or another way we say that is f prime of x. And a third way that we use it notation is df dx. So these two notations come from the fact that we've got two different people that developed calculus at this simultaneously at the same time and independently. So sometimes we use this notation and sometimes we use this notation, but it's good to be able to use both. So that's it for this video. Hope to see you in the next one.